Great. Thank you everyone for coming, and thank you the organizers for putting together such a great workshop. I really enjoyed the workshop so far. Liked the Chicago a lot. The weather is really good, the food is good, and I've been really enjoying all of the discussions and the talks so far. So for today, this is I know that there's a lot of people that are more on the math spectrum, people that are more on the biology spectrum. So this is definitely going to be a more math spectrum talk. But sort of a part of it, it's not like super hard to understand. So I hope like a general audience could understand at least like 20 minutes of the talk. And then, math audience, I hope you're able to understand all of it, because the proof is also not a super technical proof. It's very different. I'm going to present in the last 5 or 10 minutes of the proof. So I hope everyone can follow through. And if you have questions, feel free to interrupt me during the talk. Okay. So this is the talk is titled "Stable Algorithms Cannot Reliably Find Isolated Perceptron Solutions." I just put the paper title. So this paper is on arXiv earlier this year, and it's going to appear Fox 2026. This is based on joint work with Shuangping, who's a graduate PhD student at Peking University, but he's going to join Yale as my postdoc. Hopefully soon. He's having some technical issue that he couldn't come to the US now. And then Bryce, who's gonna join Yale as my colleague in the coming spring. And then Mark, who's at Harvard, but technically at OpenAI. So people have been really moving around. So the talk is gonna be centered around this model called the perceptron model. And the perceptron model, it's sort of related to the topic of the workshop. It's sort of related in some sense to the spin glass theory or statistical physics in general, and vaguely to biology. And so I hope I'm going to spend a little bit of time explaining how vaguely this is related to biology, but this is going to be a math talk. So I think I heard earlier this week that you shouldn't really start the talk by defining the model, but I'm going to do it anyways. So I hope it helps us see the connections later on. Okay. So what is the perceptron model? So let's start with the binary perceptron model. So the definition is very simple. So let's start with a discrete hypercube, which just consists of vectors of length n, each entry plus minus 1. And then let's think about m independent random half spaces, whatever they are. So S1 to Sm. And then the quantity of interest, it's the solution set S, which is defined simply as the intersection of this discrete hypercube with these random half spaces, S1 to Sm. Okay, so pictorially, this is a very simple object. Let's suppose, so we're supposed to be looking at high-dimensional object, but let's suppose that we look at a low-dimensional object to start. Suppose that our dimension is 2, then we have 4 points at the beginning. If we add in 1 half space, there's 3 points left. If we add in another half space, there's 2 points left. Add in another one, there's 1 point left. And then we add in another one, finally there's no point left. Okay,
so the half spaces are all defined by a hyperplane, one side of a hyperplane and the other.
Right, yeah. So it's like I have a hyperplane, and on one side of the hyperplane is a half space. Yeah, exactly.
Does it have to go through the 0?
Not necessarily. So I'm going to define it formally on the next slides, right? So to make sense of this mathematically, like a very simple way, how do I define a random half space? Which is exactly, so I need to specify this hyperplane, right? So one very simple way to do it is let's first sample a standard Gaussian vectors x1 to xm independently, and then let's just fix a real number kappa, and then define the half space to be the set of all theta, such that the inner product of my Gaussian vector xi with this vector theta is larger than or equal to kappa root of n. So in some sense, this xi is like the normal direction of this hyperplane, and then this real number kappa captures how large my random half space is. If this kappa is 0, then this passes through the origin. So if this kappa is very big, then I have a small half space. If kappa is very negative, then I have a big half space.
But if kappa is not 0, then it's not a half space. It's like a quarter and 3/4 or something.
I mean, it depends on how you understand half, but yeah, right? So it's like infinite anyway. So what do you even?
Okay, but there, yeah. Be clear on the model.
Yeah. I don't even know like what's a better name for this object, but it's really just like one side of the hyperplane. So, right. And then kind of the quantity of interest would just be like the intersection of these the discrete hypercube with the random the side on the one side of the hyperplane. Right. Okay, so and then there's a more like sometimes it's more convenient to pose this as a random matrix problem. So you can start with a random matrix X of IID entries, size n by n, and then the goal is to look for a binary vector theta such that it satisfies these bunch of inequalities. So I have a Gaussian random matrix. I look at the binary vector theta such that each row I want it to be larger than or equal to kappa root of it. Right. So sometimes it's more convenient to pose this problem this way. So you might wonder, why do we even consider such binary perceptron models? So and why does this talk even qualify for the workshop? So this is like how this is related vaguely. So sort of it sort of vaguely, implicitly or explicitly sort of connected to neural network. If you think of a network of this structure where sort of the nonlinearity is a step function, then if you have like random input, random output, and if you want zero training loss, it's sort of related to the perceptron model, or it's also like vaguely related to the Hopfield network in that if you want to look at sort of a memorization capacity, it's sort of related to the Hopfield network in some ways. So there are deeper connections, and in fact, sort of in the earlier literature, one of the motivation that people looked at these perceptron models is because it wants to understand neural networks or the Hopfield network. So I'm not claiming that by understanding perceptron model, we solve machine learning or we solve like the Hopfield network, but this is like a simple enough nice model that sort of already have very interesting phenomenon that starts to show up. So it motivates us to, understand it, what's going on, and then see whether it can give us some insights over more complicated problems. Okay. Great. So now this is the binary perceptron model. There's also a very interesting related model called the symmetric binary perceptron model. So now instead of looking at random half spaces, now I look at random slabs. So slab is just, I look at two parallel hyperplane that are symmetric across the origin, and I want to look at sort of the space in between that. So the two-dimensional example is like this. So I have these two lines, the space in between them. So I have intersections of these random slabs, and I want to study these random slabs, the intersection with a discrete hypercube. And then similarly, you can pose this mathematically. So instead of looking at the inequality larger than or equal to kappa, now I look at sort of my Gaussian vector inner product with theta, the absolute value less than or equal to kappa root of r. The absolute value makes this a symmetric convex body around the origin. Right. So, and this is indeed kind of, now it only makes sense to talk about kappa larger than 0, and kappa captures how large your random slab is. And then analogously, there's this random matrix formulation where you can have a Gaussian matrix and then have a binary vector. I just want the absolute value of every entry is less than or equal to kappa root of it. There's this very interesting connection of the symmetric binary perceptron model to discrepancy minimization. So it's like very nice that Ahmed had a talk on sort of a discrepancy. So it actually it's related to discrepancy minimization in the random proportional regime. So discrepancy minimization is this field in computer science where people sort of look at how do I minimize the discrepancy over different groups. I know that the audience is more like physicist, biology, or mathematician. People might not know what is discrepancy minimization. So I prepared one slide. I hope I can use one slide to tell you what is discrepancy minimization and how is it related to the symmetric binary perceptron model, and why is it useful to consider the symmetry in it. Yeah.
How important is it that these are like strict constraints? I mean, I'll use the physics language. If I soften the constraints so that I had like exponential margins or something, is it completely different?
Not necessarily. Yeah. So for example, some of these problems you can definitely consider a softer version, and then you put a Gibbs measure, you
Yeah.
put a Hamiltonian on it. Yeah, you can of course consider
These problems, they behave the same or they behave differently?
It depends on the regime. Sometimes they can be the same. Sometimes they can be different. Yeah. So I think so. The smooth so for example, so the smooth motion is kind of related to this is like hard constraint, right? So you can also pose as a max constraint type problem. Like so if I can't satisfy all of them, then how many can I satisfy at most? Then it is sort of, the soft one is sort of an interpolation between like the max version and the hard constraint version in some sense. So the max version has sometimes a different behavior. So it kind of depends on how close you are to this model.
That's its extreme value.
Yeah.
Okay.
Yeah.
But like exponential margins will behave the same or different? Like if I wanted to do a SVM or something.
If you want to do SVM,
Or vector, it's okay.
yeah, we can
go back to
can
what you're
try.
doing. I apologize.
Yeah, we can chat about, yeah, feel free to ask other questions so that I can back for more time for my talk. So yeah, we can chat more offline. Yeah. Any other questions? Yeah, there's a lot of setup in this you can change if you like. The distribution of the matrix, different values, kind of different type of inequalities that you want to post. But this is just like some good starting point to look into the problem. Okay. Yeah. Okay. So what is discrepancy minimization? Very briefly, suppose that we have a group of people, a group of n people, and suppose that they have like 3 different characteristics, whatever that means, right? So for example, what's the gender, what's the color, whether they have a pet or not. And suppose that our task is to split this group of people into 2 groups, group A and group B, such that the following holds, such that, I want the split to be more or less balanced, in the sense that, for example, the number of female in group A and the number of female in group B are roughly the same. The number of red people in group A and red people in group B are roughly the same. The number of people with pets in group A and the number of people with pets in group B are roughly the same, right? So this kind of makes sense if you want to do a A/B test, if you want to do color inference. There's a lot of natural downstream tasks that requires things like this. So if you think about this, and then you sort of think back into our like random matrix setup, what is it saying is, so if you think of each person's characteristic as one column. So for example, the first entry here is like maybe how much money the first person has. And then the second entry is like what is the health situation of this person. Then so theta is really like encoding the group assignment. So if theta I equals to 1, this is saying that I'm assigning this person to group A. And if theta I equal to -1, I'm assigning this person to group B. So this is kind of the sum, the absolute value of this, the product of x and theta is really like saying the difference of the group sum in terms of these differences, in terms of these characteristics. And I want it to be okay. So that's kind of, and then if you pose this question in a random way, in a random proportional way, this is precisely the symmetric binary perceptron model. Okay. So that's like how, that's one slide, discrepancy minimization. Great. So that finishes the definitions of these models. Now let's look at some questions. What are some questions that we want to post or we want to answer for these models? The first one is satisfiability threshold. This is a very probability word, but actually it just meant kind of when are there solutions or when are these intersections non-empty. So you can ask for what values of M and N are there solutions. So in particular, it turns out that the correct regime to look at is when M and N are proportional to each other with a fixed ratio alpha. Then you can pose the question that, for example, is there a sharp satisfiability transition? So as the system gets large, both M and N gets large, it is the case that the probability that my set is non-empty drops sharply from 1 to 0. And if this is the case, where is this transition, right? And then you can also ask some solution space properties. So for example, we can ask, how far away are these points? Are these solutions, are they close by? Are they far away? And then the reason that primarily we're interested in this question is it has some implications for algorithms. So for example, if you want to split people into groups. You don't want to do it in exponential time. You want to do it in a quite efficient time, right? Or if you want to solve your problem, you want to be able to at least find one of these assignments in polynomial time. So when are there polynomial time algorithm, and sort of how is it even related to the second question? Okay, so this is some questions that we're going to focus on. Great. There have been some predictions from physicists and have been some rigorous results development. So physicists predict that indeed it seems to be the case that there is a sharp satisfiability transition. So we can work out the exact formula through the replica method, and the curve looks like this. So for example, when kappa equals to 0, the exact half space case, turns out that this transition is at 0.833. So it's like some complicated fixed point equation that you need to solve, but after you work it out, it turns out to be around this.
Symmetric though. This is symmetric, right? Or this?
No, this is not symmetric. This is original perceptron.
Oh, yeah.
Yeah. Symmetric is here. Yeah. Yeah, so this is symmetric. Yeah, so it's kind of like monotone in a different way. So yeah, this is the not symmetric version. This is the symmetric version, and then similar qualitative behavior is true for the symmetric case. And then there have been progress along over the years that people have more or less resolved the question on satisfiability. Great. So, but there's a lot more yet to be understand. So, for example, the second structural question and the algorithm question is not yet fully understand. So, to further understand the algorithmic aspect of the question, one is naturally led to the geometry of the solution space, right? So, in particular, you can ask, does the solution space have clustering? So, a lot of these problems seems to have different structures like this. So, you might start with you don't always go through transitions like this, but a lot of them do. So, you might start with things are close to each other, and then they shatters, and then they condensate. So, there could be different phases of things. And then you can ask kind of for perceptron, is this the case that the more constraint that we impose there, are we actually seeing structures like this? And then the very kind of striking property about this perceptron model is that it is predicted that there is a strong freezing phenomenon. So it is not only shattering, it is shattering in a very strong way. What does it mean? So it says that solutions are actually isolated. And they're not only isolated, they're like very strongly isolated. So if you look at a typical solution like this orange one, and you look at the closest one to it, what are their distance? Their distance is linear in a way, which is kind of like the furthest way that they can ever get. So the distance is measured in the Hamming distance, which is just how many coordinates they differ. And then it seems to be the case also for the symmetric binary perceptron model. And then so good. So for this strong freezing property, it was proven for the symmetric case, but still open for the not symmetric case. So if you want a hard problem, I think this is a very hard problem. If you want a hard problem, you can, yeah.
Can you just go back there? They didn't literally predict all of them are isolated?
Like, I mean, it depends on what you mean. So they were like saying on the physics level, things are isolated. So yeah, it's sort of true that on the physics level, all of them are isolated. Yeah. So it's like the resolution is different in some sense.
Okay.
Yeah.
But probably, okay, you're going to tell me theorem on the next slide.
Yeah, exactly. So kind of the rigorous result is like slightly more precise. It's saying like almost all the solutions are isolated. 1 minus little o1 fraction of the solutions are isolated, and then they're indeed linear. So Hamming distance linear in a way from each other, and then it's still open for the not symmetric case. So. And then, the most fascinating part about this model, it's like upcoming. So kind of, if you step back a little bit and think about why do we even want to understand this property, right? Why do we even care about whether there's strong freezing or not? This is primarily because, it might be related to algorithms. And this connection is very intricate. So that's like that makes it fascinating. So kind of why is the strong freezing property important? So broadly, this is like broadly in disordered search and optimization problem, a long-standing belief from statistical physics literature is that sort of these properties of shattering, clustering, or freezing is sort of linked to the computational tractability of the problem, which means that whether there's polynomial efficient algorithms or not. So the heuristic a lot of the times point to this direction that if you have strong freezing or clustering, it seems to imply algorithmic intractability, meaning that there's no algorithm, no polynomial time algorithm that can find a solution in polynomial time. And then the intuition is sort of, if your algorithm, it's kind of doing some stable things or local things, and then your solutions are like these, shattered, and then your algorithm are like, doing some local stuff. It's not really making progress in finding these isolated ones. And in fact, it seems to be true for many random constraint satisfaction problems, like the random k-set and Q color. Okay, but then the funny thing is, there are algorithms. Some of them are sort of, you can run an experiment and realize that they work. Some of them are really rigorous algorithms. So then it sort of has this whole paradigm that says that there's kind of, on the one hand, the strong freezing is proven to be true for the symmetric model, and then a conjecture to be true for the not symmetric model. But then if you believe the physics heuristics, it's going to imply the algorithmic hardness. But then on the other hand, there are all of these algorithms, right? So specifically for the symmetric binary perceptrons, you have all of these famous discrepancy minimization algorithms. So how do you sort of reconcile these seemingly contradictory phenomenon that on the one hand, it seems that this freezing implies algorithm hardness, but on the other hand, there are algorithms.
Can you comment on typical versus worst case? I don't know in what sense you're saying algorithms are hard.
Yeah, this is average case.
Average case.
Yeah. So for but I mean, so these discrepancy minimization algorithms are like worst case. Yeah. So are like for any matrix. So they're like a hammer for the average case algorithms. Yeah.
But then, so I'm not totally up to date in the literature, but is there any algorithm that does better on the random case than all of our discrepancy algorithms that work on the worst case?
Yeah. So I mean, yeah. So you sort of need to be able to analyze these discrepancy algorithm very precisely. But yes, I think so. If you optimize incremental AMP optimal way, it's better than say you iterate the LP. Yeah. Okay. Right. So okay. So then if we step back, so actually, what should be the correct question that we ask? So the correct question should be, actually, how do we reconcile these facts? Or what kind of algorithms, what kind of solutions do these algorithms find? And then it turns out that there's these sequences of paper that proposes a very nice heuristic that sort of explains the resolution. In that, what's actually going on is the following. So it is true that a vast majority of solutions are isolated. So try to picture this in the high-dimensional space, right? So most of the points are like these isolated blue points. But then other than these isolated blue points, there's a very rare structure, which is this green structure, that are well connected. So kind of 99.999% of the solution are like these blue and isolated. But if you peel them away, there are these very rare, less than 0.01% of the solution that's well connected in green. And then they're saying that it's actually, what are the solutions that are defined by algorithms? There's nothing wrong with the proof of these algorithms. The algorithm actually find this green structure. So in other words, at the physics level, at the resolution, if you only look for most solution, it's kind of orthogonal to what algorithm is doing. So if you want to understand what the behavior of the algorithm is, you need to sort of zoom in a little bit more, able to look at some further structure that's very rare in my system, and then they are responsible for the behavior of the algorithm. So kind of whatever is going on the physics level, it's sort of orthogonal to whatever is going on the algorithm level. So that's the point of the. So
are these structures uniformly distributed in solution space, or do you guys have any results on like the distribution, or does Ricardo or these guys have any results?
Like in terms of like, what do you mean by uniformly?
Oh, sorry, I mean in physics language, I don't really know measure theory. It's been like,
No, yeah.
is there one of these clusters near any isolated solution or something like that? Even though they're
Like they're isolated, so there can't be close.
okay, the
Like,
order n. Okay.
Right, yeah. So I think the isolated solution should be more or less like
Uniform.
yeah, but then the kind of the connected one could be at different places depend on your Gibbs measure. Yeah. So yeah. So kind of like how complicated the system is actually coming from the connected rare one. The isolated one are just like fake.
I see. The intuition is that it's the green structure.
Yeah, exactly. Okay. So yeah.
Is the connected rare one like one way you might come up with the connected rare one is having one solution to alpha that's smaller than the target you're looking for, and then small little sprinkles.
Very good. Yeah, that's gonna give you a linear sized one, but that's not gonna give you like a very big diameter one that sort of, if you want a very big one, you sort of want it to percolate somehow. Yeah.
I see. And this is actually that big.
Yeah, it can be for a very small alpha. Yeah.
Thanks.
Any other questions? Right. Okay. So in some sense, so what algorithm is doing is this, algorithm is finding the spring structure.
So just on, and I understand you probably said it, but if I look at this is rare in the sense of the number of clusters, a small fraction of the clusters.
For the volume, the number of them. It's a discrete system. So how many of them are in the cluster? Just
you're saying
count
very small fraction of points are in the well-connected ones compared to the ones in the disconnected.
Yeah. It's actually exponentially small. Yeah.
As far as
yeah, exactly. Cool. So, okay, good. So, but these are heuristics. So our job is to prove them. So, in order to justify the heuristic rigorously, there are two things that you need to show. One thing is that you need to show that these grain structure actually exist. People aren't hallucinating. There are actually these grain structure. And then the second thing is to show that this grain structure is the one that are related to algorithms. So in other words, the isolated ones are irrelevant to algorithms. Okay. So for today's talk, so the main focus is going to be point 2, which is to show that these isolated ones are hard to find. Right, so you want to show that these are orthogonal. You want to show that first green exists, and then second the blue are hard to find. So just like one comment on the green. So you can show that actually these green exist with a big diameter for very small alpha, and then when alpha is large, you can sort of show that there is these linear sized ones by looking at like high margin solutions. Exactly. Yeah. Okay, so but then so let's look at the question of today's talk. Yeah, sorry.
What do you mean by almost maximal?
Oh, so it's just that if you think about the problem, right? It's solving an inequality, so it can't really, the diameter can't be n, because if kappa is like positive, if like a vector theta satisfies the solution, the minus theta couldn't solve the solution. So the furthest way 2 points are n. So maximal is like just a little bit below n.
But it's order n.
Yeah, order n. Yeah, of course. Yeah. 1 minus epsilon times n. Yeah.
Madness.
Yeah. Okay. So kind of like in order to show this heuristic rigorously, there's this question.
So I wanted to mention a similar problem in recurrent neural networks that that's I think exactly the same. So there was a recent paper by the group of Zakina. They showed that in recurrent neural networks with subcouplings, which are the ones I showed yesterday, you have isolated minima, which are very hard to find. They're the same class as yours, but they are connected by these slow manifolds. I think of fixed point that are barely unstable, and somehow they argue that those are the relevant ones that you need to study for computation, not the isolated minima. So there's there's kind of like a recurrent version of this
Great.
that's more of the same.
That's great. Yeah. Thanks for yeah. That's great. Which means that we have more problems to work on. So good. Any other questions? Yeah. Okay. So kind of, if you think about the perceptron model, this should be the cartoon version of the phase diagram. So what should be actually going on is, indeed there's this set on set transition. Above this, no solution. Below this, there's solution. And then the strong freezing, what the strong freezing says is that as soon as you are here, as soon as there are solutions, most of the solutions are isolated. But then kind of the whole diagram or the whole thing is like saying, whatever is related to algorithm shouldn't be these isolated ones. It should be the underlying ones. So then when the underlying ones are like well connected, you sort of have polynomial time algorithms. And then when they shatter, it's like when the overlap gap property kicks in, there's some geometric property you can say, then it should be hard for stable algorithms. So this should be like the diagram of the actual phase diagram of the perceptron model. So I want to mention this very nice work by David and Arman, who are both here. So they showed that for the symmetric binary perceptron model, it's hard to sample solutions, which means that if you want to look for a uniform random solution in the solution set, you can't really get close to it. And then they posed the question in their paper about whether it is hard to find any solution in the isolated set. So hard to sample doesn't imply hard to find isolated solution, because a priori you could have ones that are particularly easy to find. So it doesn't really rule it out this way. Okay, so great. So I want to tell you about our result. Yeah.
On the previous slide, just one, I think, nice reference. So as you said correctly, so algorithmic threshold is the one that is found by overlap gap property. And there's a work by computer scientists that proves that above this threshold, in fact, there's no polynomial time algorithms unless P is equal to NP version of it. So it's really strong reputation of the possibility of
this is a reduction work?
This is based on a reduction to the lattice.
That is, yeah. Okay.
So it's not technically P not equal to NP, but for
right.
us.
Right. Yeah. I have a last slide on my, so just to include all the references. So it's like there. So because that's a good, and that one also doesn't necessarily look at the proportional regime. So you can look at, exactly. So you can make the problem more general in this way, right?
So could you just say again what you mean by stable?
Oh, so yeah, it's essentially Lipschitz. So take it this way. So if you change the input, it's an algorithm. If you change the input a little bit, the output only changes a little bit. Yeah, that's stable. Yeah. Okay. Yeah. So I think I'm running short in time, but let's talk about the result and talk about the proof. So it's a little bit technical to set things up, but kind of what so let's for a matrix X. So this is our input. Suppose that S is the set of solutions, and then we say that a point sigma is K isolated if there's no other point in the discrete hypercube with Hamming distance K. So it's like distance K away from other solutions. Then it's called K isolated. We say an algorithm A locates a K isolated solution if its output is close to an isolated solution. So we don't even ask it to output in plus minus one. As long as you output something in the space that's close enough to the isolated solution, then we declare it success. So it's a very, very weak version of success.
Is it close in Rn or close on the hypercube?
Close in Euclidean distance. Yeah, because you don't even output. So yeah, and then the claim is that let A be a blah 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 stable algorithm. I'm gonna interpret this in a sec. Then A has probability at most 0.9 to locate a Cn isolated solution. So it's sort of this is linear in an isolated solution. So then it has probability at most 0.9 to locate it. Okay, so how stable this algorithm is like governed by this. It's very hard to read, but kind of correspondingly, let me give you this result. It corresponds to these low degree polynomials. It corresponds to degree on the order of n over log n polynomials. So to give you a sense of how good this is, so usually there is this like low degree conjecture or low degree heuristic. Usually, if the people believe that sort of degree log n polynomial corresponds to sort of the power of polynomial time algorithm, and this is degree n over log n. So it's a really big polynomial. Just means the output is a polynomial of the output is polynomial of the input.
Yeah. There exists C for which. So what is the quantifier on C?
Yeah, so it depends on. I think it depends on, so because there's these little o's and little omegas. So yeah, whatever C you put in there, it's fine.
So I get, if I take a polynomial order log n to the end, isn't that exponential? Like I said, I don't understand what a polynomial algorithm.
Here you mean a polynomial is like it's like a multilinear polynomial. You have like n variables, and each one you only take to the one.
Right.
So it's like multi-affine, meaning you could have like x1, x2, x3, but not like x1 to the 10 billion.
I see.
Yeah, exactly. Yeah.
Sorry, I understand that C depends on other parameters, but what is the claim? There exists a small enough C such that, or large enough C.
No. So any C that you put
For
in,
any C.
yeah, for any C, yeah. And then this is a very weak sense of stability. Essentially, any algorithm that you pull out should be this stable. So you can see that, for example, how much I'm changing my matrix G. So it's like governed by this eta, and then eta is like very small. So if I change
this is quantifying stability of the algorithm. I'm trying to understand the level of isolation.
Very good. Yeah, we have another theorem later on that sort of tackles different level of isolation. Yeah.
Wouldn't there be some like boosting so that this probability, instead of being like at most 0.9, is like at most epsilon?
Very good. No, we can't do it. So and you can see why in the proof. Yeah.
Okay.
Yeah. But I don't know. Can I have a few more minutes to explain the proof? Yeah. Yeah. Okay. Yeah. Any other questions? Yeah. This is just like because it's so for not experts it might be a little bit hard to explain, but for a expert, yeah. So it's like. There's a theorem in the next slides, 2 slides later, about how isolate you want it to be, and it's related to the stability of and then low degree. Yeah, it's just sort of to showcase that it's a really weak sense of stability. You just change the matrix a little bit, as long as the output wouldn't jump too much, then you're good. That's the statement. And then there's also, if you don't like the 0.9, there's sort of a residue of it here, which sort of says that, if your algorithm, let me maybe just say it in word. If a stable algorithm finds some solution with high probability, then it finds an isolated solution with negligible probability. Right. So for example, all of these algorithms that are shown to succeed in finding solutions like key mirage, or so like the symmetric ones. So all of this discrepancy, they can't find isolated solutions with probability more than little 1. Yeah, this is the residue of the 0.9. And then there's this scale dependent result, which is sort of if I K isolate, it's just like distance K, and then it sort of factors into the stability through this relationship essentially, right? So you can get to very, you just can get close to it doesn't have to be linear isolate the point. Yeah, that's to answer David's question. Yeah. And then there's also a version for the symmetric perceptron in general. I'm gonna skip this. Blah blah. Okay. Proof. Maybe I'll spend 5 minutes explaining the proof. At the beginning, I sort of thought about using OGP to prove this, but it doesn't seem to work. It's very hard to make use of the isolation. After you condition on the fact that this is isolated, all of the moment computation breaks down. I find it very hard to make use of the condition. So what we did instead is something very different. And it's not a very complicated proof, so I hope everybody can follow. Let's get started. It's a proof by contradiction. Suppose that there's a stable algorithm. Let's say it outputs an isolated solution with probability more than 0.99. Okay, then I give you a matrix X. I look at the output through the algorithm. Suppose it's this point sigma. Okay, now I look at the little ball of a little radius Cn/3 around it. So this is my ball around it. And then I look at a slightly correlated matrix, called it X tilde, because I want to change it a little bit to make use of the stability. Okay, now I claim that condition on the randomness of X, so sort of all of the statement where all of the randomness going forward is from this actual randomness X prime that's coming. Okay, so with probability more than 0.99, I claim that there is exactly one solution in this ball with respect to X tilde. Okay, so why is this the case? Because first of all, let's just look at the output through this algorithm of the perturbed matrix X tilde. Let's call it sigma tilde. Because of the fact that this matrix is stable, so I know that the sigma tilde and sigma needs to be close to each other, right? So which means that the sigma tilde needs to be in the ball. So of course, there's at least one solution in the ball. This is because of stability. Okay. Now, because of isolation, I know that this sigma is an isolated solution. So in particular, how isolated it is isolated here. So it's also in particular isolated in this ball, right? So in particular, this shows that there's at most one solution in this ball. So stability implies that there's at least one solution, and isolation implies that there's at most one solution. So putting them together, I just know one simple fact, which is my claim that there's exactly one solution to X tilde inside this ball. Okay, so that's we're on the same page now. Now, this feels very weird because why this feels weird? Because if the claim were true, this would imply the following. Let's split the ball into two parts, left and right. Let's call it C1 and C2. Okay, and then let's call like D1 and D2 like the number of solutions on the left and the number of solutions on the right. Okay, and then the fact that we say that there is exactly one solution in the ball implies that if there's one solution on the left, then there's no solution on the right. Or if there's zero solution on the left, then there's one solution on the right. Okay, 1, 0 or 0, 1. Right? So in particular, this implies that the number of solution on the left and the number of solution on the right needs to be negatively correlated somehow, right? So because this is kind of, 1, 0 or 0, 1, so they needs to be negatively correlated. But if you think about this, they can't really be negatively correlated. Why they can't be negatively correlated? So intuitively, you take 2 points, like 1 point here, sigma 1, like theta 1 here, and the other theta 2 here. This is a very small ball. So these are 2 points that are very close to each other. If this one is a solution, in principle, it should really be helping the other one being a solution. And there's indeed a way to make this intuition rigorous, which is essentially FKG inequality, but in a fancy version. So we find this paper called Pete's inequality, which is essentially saying this. So yeah, it's kind of a generalization. It's a higher dimensional version of the FKG. So which is saying that, if you have coordinate-wise increasing functions and you have like non-negatively correlated Gaussians, they needs to be positively correlated if you pass it through functions. So in particular, you think about how do we use this sort of FKG in our proof. It's just for 2 points theta 1 and theta 2 here, because they're close, if I look at the inner product of my Gaussian row with this theta, these are correlated Gaussians, non-negatively correlated Gaussians. And I pass it through these channels, which is indicator of whether this Gaussian is larger than or equal to something. This is indeed a monotone function. So they needs to be positively correlated. So sort of whether points on the left and positive points on the right, they should be non-negatively correlated, governed by these FKG. So then kind of the number of solution on the left and the number of solution on the right needs to be non-negatively correlated, which violates the negative correlation that we had in the first place. So this gives us a contradiction, which means that there can't be any stable algorithm that reliably locates isolated solution. That's it. So it's just it's a very soft statistical physics FKG argument, but it's good enough to give you the argument. So and sort of to answer Rada's question, why there's like you can't really get down to little O1 because if you pretend solutions are like following a Poisson point process, then things were like zero, like independent in some sense. And then so like for Poissons, it could have a probability constant at 1. So it's not you can't really, there's no hope to pull it down to little O1 in any sense. So there's an intrinsic barrier for using specifically this argument to go down to little O1. Yeah, and then for symmetric you need to do a little bit else because it's not monotone anymore. Okay, so let's wrap up. So today we've learned about the binary perceptron model, which studies the intersection of these random half spaces. It's a very nice random constraint satisfaction problem that connects the neural networks, statistical physics, and discrepancy minimization. It's in particularly interesting because it breaks some of the intuitions that strong freezing holds, yet there are polynomial time algorithms. And then we complete the picture by showing that stable algorithms, including low-degree polynomials, cannot reliably locate isolated solutions. So whenever such algorithms succeed, they must be finding these atypical non-isolated solutions. Okay, and then the proof is based on this negative correlation, where like anti-concentration, which contradict this FKG type inequality. And then there are some like future directions that you can consider. For example, we can look at the spherical perceptron, which is instead of having binary ones, what if I'm on the sphere, what happens? And then kind of you can also consider near isolation. If I have a softer version, what happens? I try to improve the 0.9 to little O1. So I have a ongoing work that for looking at online algorithm. For online algorithm, there's some special structure that you can use that we can get it down to O1. Yeah. So, but we're writing it up. Please don't scoop us. Yeah. I'm gonna. Yeah. So and then generally there's like kind of this is not the usual OGP approach, and whether this kind of anti-concentration type inequality could be used to apply to other general, other average case problems. Yeah, that's it. Thank you very much, everyone.
Just for
Yeah.
Just a question on the thing you didn't talk. Do we have any information on the geometry of this non-isolated structure?
So, I mean, kind of like yes and no. So it should be some tree structure, ultrametric tree structure in some sense.
Nothing is really known.
Like to some extent. So you can, yeah. So it depends on like what you mean by known. So there are like some physics predictions. There are some sort of descriptions, but not like very, not a very complete understanding.
The diameter is linear. The diameter.
Yeah, but like other than that, if you want to really understand what, like how does it look like, it's not well understood yet.
So come back to just a basic thing on what you mean by stable. So you're doing a perturbation which scales in how as n gets large.
So
perturbation sometimes is order 1 but small.
Yeah. So on the order for us is log n over n, so very small. But then you want the change to be not linear. That's it. Yeah. Not you. So I changed like 0. So I changed like log n over n, and I don't want the change to be 30%, for example. Yeah, that's stable. So like that level. So it's like really change a little bit, and it wouldn't jump too much. Then you're good. Yeah.
Cool.